Do you want to handle the table, Tony?
I'll let you do that.
I'm going to have you do it.
Okay, I can do it.
Because I will write in it. So after we do our introductions, the intros, when I put you on the spot, you'll take over from there.
Okay.
All right. I'm going to play some music. Good morning to everybody. We are so glad that you're joining us today as we continue our week of connecting calculus AB to BC, where each day we're taking one topic from AB, doing a couple of quick checks, refreshing how we can work with those problems, and then looking at how we might connect that one topic to other topics throughout the course of Calc AB and those BC unique topics all in one to get you prepared for the 2020 AP Calculus BC exam. So we are so glad that you are here with us today. We've got an exciting show. I'm going to start calling these shows, I guess, and not just lessons. An exciting show talking about particle motion and making all kinds of neat connections. I feel really excited about the problems that we have today to share with you. So as always, you can find our materials in our Dropbox, and they are hyperlinked underneath the video. You'll see there all the materials we're doing today. Tons of extra practice problems as well as solution keys loaded up there. So make sure you take a look at those and follow along with us if you can. I am Brian Passwater, a teacher at Speedway High School, joined by my, who I thought was my really good friend, Tony Record, but I'm starting, Tony, to question this a little bit. Yesterday, I shared kind of like an embarrassing story about a letter that I thought I had received from the College Board when I was a young AP teacher, and how excited I framed it. I was so excited, and my students pulled a prank on me. It wasn't actually from the College Board. And I thought today I'd share another quick embarrassing note because I do enough of them that I can share them pretty much every day for the rest of my life. A couple days ago, maybe Monday, we were live on the air, you and I, right, as always. And I did the whole session. And then afterwards, my wife and I went for a quick walk around the neighborhood. And because these are early mornings, just as 9 a.m. Eastern, but you and I get up, pretty early because we meet beforehand and kind of hash out some things and things like that. And my wife's still in bed when I get up. So I try to be quiet, keep the lights off, and I get dressed in the dark. And I come up here and my eyes are kind of tired and crusty still from when I wake up in the morning. I went through the whole session. Went through a walk with my wife afterwards, and in the afternoon, and she noticed in our walk that my shirt I was wearing was literally inside out. She says, "Do you know your shirt's inside out?" I was like, "Oh, I didn't notice that." And it dawned on me. I did an entire lesson on here on Monday. I think it was Monday, with my shirt completely inside out. And you're my wingman, Tony. You're supposed to catch these things in our live Zoom. What happened there?
I just thought it was like a new fashion statement. I thought you were really trying to show off your drip.
Oh, my
that's
drip.
What I thought it was about.
Okay. Yes. Yeah. So yes, I think the use would say that I am showing off my drip, right? So I definitely am that. So that's my embarrassing moment for the week. But other than that, hopefully we can save the embarrassment for the rest of the show, and I'll have to wait till tomorrow to do something more embarrassing. But I am excited today, Tony. We got some particle motion. I know that you're going to walk us through a really quick sort of formula sheet about what the kids need to know. And then we're going to jump right into it today because we got so many problems that we want to get to. So we want to get through as many as we can in this next 45 minutes.
All right. So yeah, we've got this opening page of your document shows you sort of your one-stop shop to all things particle motion. Well, I got to be careful. When I say all things particle motion, we really are only talking about particle motion as it relates to the rectangular coordinate plane. There's so many connections that particle motion has with parametric, and that typically has been the often go-to particle motion question on the BC exams in the past. But since we're not going to be dealing with parametric equations on this particular year's exam, you can narrow your focus to the rectangular world. And that's what this table pretty much talks about. So we're going to call this the particle motion reference information. And a lot of this is likely information that you've already seen in your course, but it's likely that it was taught maybe very early in the year. You know, you, of course, being BC students, maybe some of you are taking BC as a second year calc course, and at which point a lot of this was probably taught to you last year. For those of you that take your BC course all in one year, your AB material and your BC material together, this was still probably taught very early on. So you know that, x of t is your position, and you take the derivative of position to get velocity. And of course, you take the second derivative of position or the first derivative of velocity to get acceleration. Those are your basic foundation, right? But we also have to remember these various things about your direction of motion. And it's really just a matter of knowing what the sign of the velocity is. If velocity is positive, we know that that's a situation where the particle moves to the right. If velocity is negative, we know that's a situation where the particle moves left. Particles won't move any other way on this year's AP exam. We don't have to worry about things moving up and down, falling from the sky. There's a separate AP exam that talks about that, and that's called AP Physics. Speeding up and slowing down, very big idea when it comes to particle motion. And your big focus is going to be basically talking about the signs of the velocity and the acceleration. If those two signs are, excuse me, what I call in tandem with each other, that basically means that if the velocity is a sign that's, say, moving this direction and the acceleration is the same, it's like there's a force that's pulling on that particular particle that's just going to tend to make it go faster. But on the other hand, if the velocity is, say, going in this direction and the acceleration is another force that pulls it from the other side, then obviously that's going to slow down that particular particle. So you're going to look at the comparison of the signs to determine if the particle speeds up or slows down. Position at time c, very important concept that deals with, yes, the fundamental theorem of calculus, which we talked about yesterday. So we're going to use this idea to find that the position at any time c is just going to be a matter of taking the position at the beginning of that time interval, a in this case, and then adding that accumulated change of position. And that's what the integral of v of t from a to c is going to be here. Now, if we're talking total distance traveled, that's a little different when we need to invoke the whole absolute value idea, because we don't want this velocity to be kind of positive and negative and going all over the place back and forth, because that's not going to give us a very good depiction of total distance traveled. So we take all of those chunks of time that maybe the velocity was negative, thus the particle moving left, and we sort of trick it into thinking that the particle was moving right that whole time, and thus we can accumulate a total distance traveled. Okay, particles change direction when the velocity changes signs, right? We've kind of talked about that before. And then, of course, the speed, sometimes we call that the magnitude of the velocity if we're dealing with the vector world. But when we're talking about just the parametrics, we're okay just to call that the absolute value of that particular velocity. And of course, if we integrate that, we'll get total distance traveled. So let's go ahead and take a look at our first quick check here. And I'm just going to do a couple of parts. We're just going to kind of do bits and pieces of our quick checks because we got some wonderful free response questions coming up. I think that you're going to really like that. Our BC2 is a doozy. It's got a part 1, a part 2, and a part 3 with separate subparts and a lot of things going on in that problem, from a particle moving to popcorn being sold at a halftime of a football game to a young male human growing through their first 13 years of life and beyond. So lots of neat things in store. So for quick check 1, for the time interval 0 to 12, we have a particle that moves along the x-axis. The velocity in meters per second of the particle is modeled by the function v of t, which is shown in that figure above, and it consists of our 4 line segments and that quarter circle that happens to be centered at 10, -3. The position of the particle x of t at time t equal 3 is going to be -2. So our first question is, for the time interval 0 to 12, when is the particle moving left? And we have to give a reason for our answer. So this is where that communication piece comes into play. So as we look at our reference chart, and you're welcome to kind of flip that back and forth, if you're able to even, take it off to the side. Maybe don't even staple your packet together, but have that off to the side, and you can always refer to it as you're working through these problems. You may have noticed that that particle is going to move to the left when the velocity is negative. So we just simply look at our graph. It is a graph of velocity, and we can see it's from this time interval, 0 to 3, that graph lies below the x-axis. And then again, we see that happening from the interval 9 to 12. All right, so what we could do, if you want to write this really kind of nicely, you can say the particle moves left. And then it's probably nice to use a good preposition here. We're going to talk about a time interval. So I would avoid the word at and maybe use the word on, use the word over, something that connotates an interval. So we could say on the interval 0 to 3. And notice I don't really want to include the endpoints here, because at the endpoints, we know that the velocity would actually be on that t-axis, which makes it a 0 velocity, and it's a situation where we're neither moving left nor right. And then again, we see from 9 to 12. And so there's our answer, but we need to connect that to a reason. And the reason would just simply be because v of t is less than 0 on those intervals. You don't even have to say that your v is equal to 0 at those endpoints, because it's implied in this particular instance because of the intermediate value theorem. So that would take care of your part A. Part B is a wonderful part that I would like to leave it to you to kind of look at a little bit, finding the position of the particle at time 12. But if you use your reference sheet, you can see a very nice way to get into that particular question. And you're always going to be able to check these with the keys that we have posted here, in about 24 hours or so. But I would like to talk about C, because we've just begun to address this issue with this concept here just recently. And I have, Brian and I always have certain predictions about the AP exam. Of course, we don't know exactly what you're going to see, but I'd like to talk a little bit about what our feelings are with this particular concept. So we're trying to find 1/9 times the integration of v of t from 0 to 9. And then we want to use correct units and interpret the meaning of this integral within the context of the problem. So the first thing that we want to do is go ahead and evaluate this definite integral. So I see that 1/9 as nothing more than just a constant that I'll bring down. And then I look at this integration of v, and I have to scratch my head and think, well, I can't really truly integrate v, because that's going to give me a position. And I really don't have a lot of information about position in this problem. In fact, I really only have one piece of information, and that's the position at time 3. So what we need to do is think about another way to evaluate this definite integral, tying into what we talked about yesterday with fundamental theorem. We're just going to find the area under the curve v of t, between the curve and the t-axis here. So as we see, this area from 0 to 9 consists of 2 parts, and I'll just kind of shade in the first part. And this sort of magenta colored part is kind of interesting, because we see that it lies below the t-axis. And then as I move more forward, I move into this blue shaded region, and that's going to be, of course, above the t-axis. So we just have to remember that we treat any area that's below the axis as negative and above the x-axis or t-axis as positive. So moving into this problem, we have this area of this magenta colored triangle that will be negative, and we have the formula 1/2 times the base times the height, and the base is 3, the height is 2 in this case. And we want to double check and make sure that our scale is all uniform, which is going to be very important in a problem that we see later on. And then we would add, and you can break this figure apart a variety of ways, but I would trust by now we're starting to feel pretty comfortable about the formula for the area of a trapezoid. It's kind of a big deal in calculus, right? So we can use the trapezoid formula. So 1/2 times the sum of the bases, and looks like we have a base here at the bottom that's a length of 6, a base at the top that's got a length of 3, and then the height of this trapezoid is going to be a 2. All right, so when we put all of this together, we end up with 1/9 times the quantity. Then we have a -3 here, and we have basically a 9 at that point. And then we could go ahead and simplify. This is going to be 6/9 or 2/3. And again, we say this often, your degree of simplification is really up to you. You had us at this first step. This would be acceptable because it is a numerical value that would be equivalent to this 2/3. But now we have to use correct units, and we have to interpret the meaning of this integral in the context of the problem. And what we want to train all of our students, Brian and I, in our own classrooms, and we'd like to do the same as you, and it's likely that your teachers have already done this for us, but anytime that you see an integration expression with that coefficient of this form, in other words, you see that the difference between the boundaries is what resides in that denominator underneath a 1. So in other words, you see this sort of 1 over b minus a times the integral of a 1, an integral from an a to a b of, well, I'm just going to say some function, right? Some function of some variable. This is always just going to be interpreted as the average value of that function. Insert the name of the function, whatever it depicts in the context of the problem. In this case, that function is velocity. So when we go ahead and interpret this, we could just say this is the average. Now, if you want to say the average value of velocity, it would certainly work. It's probably a little overkill on the words because you could just simply say the average velocity. Now, there's an acronym that you can use called NUT that a lot of teachers use. If you've never seen this before, maybe it's likely you've seen something else similar in your classroom, but we kind of let the N stand for the noun or the number in the problem. U is the units, and T is the time. And those are the three things that you must address whenever you're interpreting the meaning of whether it's a derivative or an integral. So I'm starting the building blocks of the noun part, right? The average velocity, and I know that's going to be 2/3, so that sort of takes care of the number. And we need to get a little bit more context. How about we say the average velocity of the particle? That kind of gives us a little bit more clarity. Okay, well, what is that average velocity? Well, we just computed it to be 2/3. Okay, but now we need that unit. And so the unit here, well, if we integrated the velocity, now remember the velocity was measured in meters per second. So I guess if you go up to this particular graph, we know that this was meters and this was seconds. And by the time that we found area, which is what the integration process is, we have meters times second, right? All right, well, we've got this meters times second, great for this area, but then all of a sudden, we're going to have to take into consideration what we're going to be doing with this 1/9. Well, wait a minute, that meters times seconds is also going to have to be tempered with the fact that we have this dt. So in essence, what we've just found is meters, right? Whenever we integrate this velocity, that second drops away, all right? Because we have meters seconds over seconds. The meters drops away, but then this division by this new element of time is going to invoke that new idea of seconds being in the denominator. So the average velocity of the particle would be 2/3 meters per second, which is probably not too far-fetched because that's kind of what you would think velocity to be measured in anyway. But we're not done yet. And the reason we're not done is because we don't have the T element. And this is usually one of the most common ways that a student wouldn't earn full credit on the interpretation. So what we'd have to do is know that this is the interpretation of an integral, which means we use an interval to depict what's happening. So we want to use a very good word like on or over. I don't like the word at to interpret it, the meaning of an integral. And we'll say we could use the word interval. That's fine. Let's go a little bit more powerful. And we know that we're starting at t equals 0. We're going to t equal 9. And you do want to go ahead and label the time element here, which we know is in seconds. And that would be a really strong argument. That would be a really strong exemplary answer for that interpretation. There are a few things that you could alter to still get full credit, but these are the kinds of things that we like to show our students. We like to show them the most exemplary answer to hold that bar really high. All right, I think we're going to move on to quick check 2, if I'm not mistaken, and I believe Brian is going to take the lead here. Brian.
Perfect. So we're going to go through this one a little bit more quickly than the first one, 'cause we want to make sure we have some time to get to these, at least a couple of these FRQs that we have at the end of the lesson today. So looking at quick check number 2, so Tony looked at an example where it was a graphical example, right? So we're always trying to show you different representations, we would call them. So sometimes you might get a graphing problem, or you might get a table problem. I think with the way this year's exam is going to be done, there's probably a certainty that we're going to have a lot of graphs and tables on these two FRQs, because those are two ways that we can, generally speaking, eliminate the use of technology as an aid to students, right? And so those are good examples that I think might prepare you well for this year's exam. So quick check number 2 says, okay, we have a new particle now. It's moving along the x-axis, kind of similar to what we had before, and the position is x of t, and we're doing it for 6 seconds. And then we have in this table the position, x, the velocity, and the acceleration. We have all three things given to us. Now, we don't know what's happening between those values, right? That's one of the big mistakes I think that students make, is when you're working with a table, generally, you don't know what's happening between each one of those points. And sometimes we make assumptions about what's happening, and we can't do that. Students might say, well, here, the velocity was 0, and then it was 5. So the velocity increased, during this time to 5. We can't say that, because it could have gone up and down a whole bunch, right? Because we don't know what's happening between 0 and 1. And so there's some things we can figure out from tables. This is where your existence theorems come into play a lot. Intermediate value theorem, mean value theorem, those kind of things work well with tables, because they know even with only a little bit of information, we can still make some guarantees. So when you see a table problem, I tell my students, it means we're probably going to be doing some approximations. Since you don't have all the information, you don't have a graph or the whole equation, you might be able to approximate some answers, or you might be able to do some existence theorems, guarantee some things like IVT or MVT. In this case, we're going to look at a unique problem that Tony mentioned on the first slide, but we haven't seen an example yet. Is the speed of the particle increasing or decreasing at time t equals 4? And I think part of the confusion is that when we drive a car, a lot of times when we push the gas pedal, right, we say, oh, we're accelerating. And we think the gas pedal is accelerating. And so what happens is we get this misunderstanding that whenever you go faster, you are accelerating, right? You have a positive acceleration. And that's not actually how it works, right? Acceleration is any, or positive acceleration, or acceleration in general, is any positive change in velocity. So it turns out in your car, your gas pedal is an accelerator, but so is your brake pedal. Every time you brake, you're also accelerating. And your gas pedal doesn't mean you are accelerating positively, and your brake pedal doesn't mean that you're accelerating negatively. It depends on which direction you're moving in the first place, right? And so when somebody says, is a particle speeding up or slowing down, the big misunderstanding is, oh, that means when you start going faster and faster and faster, it means that you are going, you're speeding up, right? But what we have to be careful for is that when we start talking about speed, it requires us to consider not just the velocity, we have to also consider the acceleration, both. We have to take both of those things into consideration. Velocity tells us which way we're moving, and acceleration tells us sort of like which way we're pushing. Are we pushing forward? Are we pushing backwards? And those two things combined will determine whether you're speeding up or slowing down. And so if we look at the time t equals 4, we're looking right here. And we know from the table that our velocity at 4 is -3. So v of 4, our velocity is -3. And a of 4, our acceleration, is going to be just -1. And so what's happening here? So the negative velocity, and by the way, our position happens to be at -2. That's pretty much irrelevant, right? We don't really need to know where our position is, but at time 4, we're at -2. Here's my particle. Negative velocity means I'm moving toward the left, right? We have a velocity that's negative, so we're moving toward the left. And then think about what the acceleration is telling us. Acceleration tells us, which way am I pushing you, right? Imagine this particle is moving toward the left, and then the acceleration is negative, means we're pushing it toward the left, right? Whenever your acceleration is negative, it means you're pushing toward the left direction. And so not only is my particle moving left, the acceleration is pushing it in that same direction. Our acceleration is negative, which means it's pushing toward the left. And what's happening? You're moving left and someone pushes you left. Imagine you're walking somewhere and someone comes behind you and pushes you in the same direction. It doesn't matter which direction you are going. If someone pushes you in the same direction you're trying to go, you're going to have that kind of jolt, right? And you're going to be speeding up when you do that. And so this is why if something is speeding up, we look at both acceleration and velocity. And since they're both negative, we're actually going to be speeding up. And so we can say on a problem like this that the particle is speeding up at t equals, what was that time? 4. And then our reason will just be because v of 4, our velocity, and a of 4, our acceleration at that time, have the same sign. So whenever they have the same sign, it means we're pushing in the same exact direction that we're moving. And if they have opposite signs, they're kind of conflicting. You're trying to go one direction, but you're pushing in the opposite direction. And when that happens, no matter what, you're going to be slowing down at that time. Then we're going to mention part B here, and we're not going to go in depth on it because Tony is going to hopefully get to a nice problem that will address this in a more contextual way. But here we have this integral of the absolute value of V. And so when you're doing a Riemann sum, you got to be careful on your table because our table is velocity, right? And sometimes we get so used to making a Riemann sum, just adding those numbers up, which is what you would do if you were integrating velocity. But here we're not integrating V, we're integrating the absolute value of V. So we have to keep that in consideration when we're adding these things up. And then it would also ask us to interpret the meaning of this. Hopefully you kind of remember when we integrate absolute value of V, you're going to be coming up with a total distance traveled question. There's a difference between integrating V versus integrating absolute value of V. One of them is your displacement, and then this one is going to be our total distance traveled. So I'm going to leave that one for you, but I wanted to kind of lay that as some groundwork to get ready for what's going to be coming up here in a little bit. And then finally, quick check 2, part C says, when do we know the particle's moving toward the origin? I like this example because it reminds me of the speeding up and slowing down problem. And we see those speeding up and slowing down problems on a lot of previous exams, but we don't see a whole lot of questions like this in recent years. And so I could see this being a nice little twist the College Board could throw on one of these tests. And again, it's important because it requires 2 things, right? Just like speed does. If you're moving toward the origin, if you say, oh, you're moving left or you're moving right, you don't know if you're moving toward the origin or not. It depends on where you are, doesn't it? And so if we're going through this problem, let's take it at these different times. Let's say, look at what happens at t equals 0, right? I like to always draw pictures. It helps me know what's happening. At time 0, we know the particle is at -1, right? So which means the origin is here, right? Our position is -1, but what's our velocity at that time? It's 0. So we have a particle here. It's not moving at all, right? It's just sitting still. So it's definitely not moving toward the origin. So that one definitely is going to be out. What about at t equals 1, the next particle? Now our position is at 3, according to our table, right? So our origin now is going to be over here because we're on the positive numbers. So our particle is sitting right here at 3. But which direction is it moving? It's got a positive velocity, which means it's moving toward the right. Well, we can easily see from our picture, we're moving away from the origin, right? So that one's definitely not going to be it. What about t equals 4? Well, at t equals 4, our position now becomes -2, right? So here's our origin over here. And then which way is it moving? The velocity is negative as well. So which way we're moving? We're moving left. Negative velocity means you're moving left. Oop, guess what? We're still not moving toward the origin because we're left of the origin and moving toward the left as well. And so I'm hoping, unless I made a mistake, that this last one is going to maybe work out. And so at time equals 6, we are at -4, right? This is where we are. So our origin is going to be over here in this case. In which direction are we moving? Well, our velocity is a +2, which means we're moving toward the right. And now all of a sudden, guess what? We are moving toward that origin, but we could only figure that out because we considered where the position was and the direction of motion both. And so when you see problems that maybe look a little bit different than what you've seen before, it's kind of a little bit confusing, draw some pictures, draw some sketches to help you get an idea of what's happening. So this is the only time that we can guarantee it is. Again, it could be happening other times that we don't know what's going on in between those numbers. That's why it's the only time that it's going to be certain. So that's going to be quick check number 2. And I'm going to leave off the explanation part of it just for time's sake, but that'll be in the answer key. It'll be very similar to how we laid out the explanation of speeding up and slowing down. But Tony is going to walk us through some parts of another FRQ that will connect some particle motion to some other ideas as well. So Tony, what do you got for us here?
Yeah, in fact, I may do maybe more than just walk. I may run you through a couple of parts of a BC1 here because we got some really neat things we'd like to get you exposed to at the end. But in BC1, what we've got is a graph of velocity again. I'm going to paraphrase some of the stem of the problem. And we have these signed areas of this value of 6, the soon to be -5 and 18. That will lie between this curve and the t-axis, the time axis. And then something kind of funny is happening here. After time 9, right here, we're redefining the velocity equation for this particle that's moving, this v sub p particle, and it's going to be called 45e to the negative k times t power. And all we know about k is it's some constant between 0 and 1 inclusively. And we also know that the initial position of the particle at time 2 is 7. Now, I'm just going to gloss over 3 really quick parts, and I may not write a whole lot here, so you might just want to listen, and then you can kind of fill in some of the packet when you work it on your own later. But part A, just pretty simple question. Find all the times t on the interval 0 to 9 at which the particle changes directions. Give a reason for your answer. Well, if you remember to our reference sheet, particles will change directions when the v of t changes signs, right? We change from going to the left to going to the right or vice versa. So how do you interpret that graphically? Well, you just simply look and see where does this curve cross the t-axis. And we don't mean bounce off of the t-axis, we mean physically move from the upper side to the lower side or vice versa. So the answer to A is 2 and 5, and you could write that up. And the reason would just simply because v of t changes signs. You don't even have to say that v of t is going to equal 0 at 2 and 5 because it's implied by the intermediate value theorem. Although if you say that, it's a strong argument and it won't hurt you. Part B. Part B asks to write an expression that involves an integral that gives the position x of t and use that expression to find the position of the particle at time t equals 0. Well, once again, your reference sheet at the beginning of your packet will really walk you through the process of finding any position given the information that's provided in this stem. Now, with this particular setup, we're trying to find an expression for x of t. So we'd really like to know, hey, where is this particle located at any time t? In order to be able to figure that out, you're going to have to know where the particle starts. And we only have that piece of information provided at time 2. So we know that x of t is going to start with this x of 2. And then from there, we will accumulate some more positional change. And we do that by using a definite integral, starting at where we begin with our initial time, 2, and then we take this up to an unbeknownst time to us that we're going to call t. Okay, well, that's kind of interesting because this is working out to be a function in terms of t. Well, what is it that we integrate? We of course integrate the velocity. Now, I don't want to go into a lot of detail about what the heck do we put here, right? What goes into those 2 spots? Because we could have an all-day discussion about this and we'll circle around and really accomplish very little. A lot of times teachers say, oh, we must put this dummy variable. We must put some variable there that isn't a t. I would certainly want to stay away from maybe using x. Maybe k wouldn't be such a great idea to use. So really, it doesn't matter what you use. In this case, maybe I use s, right? But it's just that. It's a dummy variable because this is going to be a function in terms of t anyway. As soon as we integrate this, aren't these s's going to disappear and this t is going to pop into play? Now, that being said, what if a student or a teacher for that matter used t in these 2 cases? It's not the end of the world. It's okay. The problem still makes sense. We could go around and around. We could talk about, oh, the order of operations and how that impacts the problem. So I think a lot of times we make too much of a deal out of the use of the dummy variable here. Okay. And at that point, you would just go ahead and say, well, if I want to find the position at time 0, then we just replace the t with 0. What's nice about this expression is that you can use it to find the position virtually anywhere now. That's what's great. And when we go into this particular graph, we see, oh, well, if we want to integrate from 2 to 0, well, that's a little backwards, right? So no harm in just switching those boundaries from 0 to 2 to kind of treat it a little bit more conventionally. Of course, that brings out a negative sign. And at this point, we could go ahead and probably find that area fairly easily, right? We have that set up to be a 6. Remember that x of 2 was 7. And of course, 7 minus 6 would be 1. And that would be the position of that particle at time 0. And then the very last part of this problem is kind of interesting. It's sort of a teaser. Make sure I get to the right part here, part F. It's sort of a teaser for tomorrow's lesson. Let R be the region bounded by the graphs V of P of T and the T-axis from 9 to 15. Write, but do not evaluate an integral expression that gives the volume of the solid generated when R is rotated. I'm just going to kind of paint the picture here for you. Basically, we could extend this axis out to 15, and we could say that this graph 45e to the negative kt, I don't know what it looks like, but you know what? I really don't care. I do know that it's fairly well behaved and it's not going to dip below a very important line that I'm going to be using in this problem, and that is the line v of t equals -1. Well, here's that horizontal line. Let's just put it down here. We know that it's going to be below the t-axis. So this will act as our axis of revolution, okay? And then if we take into consideration this region that we're going to bound, we would have to set up some representative rectangles. And let's go ahead and maybe just really quickly show you that region, because it says this graph is bounded by the t-axis. So maybe it looks something like this. I never did real well coloring in between the lines, did I? That's about as good as I can do there. So what we've got going on here is a decision. A decision must be made about how you would set up this volume. We have disk method and we have washer method as our two primary go-to procedures for finding this rotational volume. And in this particular case, you could set up a couple of representative rectangles. The first one might look something like this. We'll go into a lot more detail with this tomorrow, but I always like these rectangles to be set up so that they start from the axis of revolution. The first one would go to the farthest boundary, which is the curve itself, and we can call that capital R. And then the next one will go to the nearest boundary, which would be the t-axis in this case, and we would call that little r. And then it becomes a matter of finding out what the expression is for capital R, top minus bottom, little r, we could do top minus bottom. Assemble that correctly into our nice volume formula. Don't forget the pi, everybody likes pi, and boom, we've got a great setup for our volume. But like I said, I didn't want to go into a lot of detail with that because that's going to be our teaser going into tomorrow's lesson. And this is going to give Brian a chance to kind of move on to the rabbit hole that we call BC2. Is that right, Brian?
Yes, let's go ahead, Tony, and I'm going to skip over here to BC2, and only going to look at a couple of parts, but I want to make sure that we understand at least what the STEM is talking about, because we're going to be using this multiple ways. So the big idea is this. Particle motion is always a big, important idea. We've seen a lot of AB exams where particle motion is one of the entire free response problems is revolved around particle motion, and on BC, a lot of times, that parametric idea is a lot of times one of the free response questions. Well, we're confident there won't be a parametric free response since it's not on this year's exam. We're probably not going to see an entire particle motion question. So we're probably not going to see an entire problem that's, hey, this is particle motion. It might show up as like a part C or a part D in the midst of a bigger idea. And so that's what we tried to do here with BC2. And we have 3 parts to it, and each part has like multiple subparts. It's the gift that keeps on giving. But here's what they have in common. All 3 FRQs use the same table. We have a table of values for a function f given, and then we're given a graph of a function g. And then all we know from the STEM is that f and g are continuous as long as for all values t greater than or equal to 0. And then we have a couple of values given to us in the table for f, and then a portion of the graph of g, meaning this graph of g will keep on going. And then we also know that when t is positive, the function f is increasing. So f is always increasing for all its domain. So we're going to start by looking at a little particle motion idea. So we have 2 particles, particle P and Q, and they're moving along the x-axis. So now we have the idea of 2 particles working together. and they have positions x of p and x of q, and then their velocities are going to be v of p and v of q. And essentially, what we're doing is we're defining this table is going to be the velocity of particle p, and this graph is going to be the velocity of particle q. So these are velocity equations that are given to us. And then we're going to look at a couple of different pieces of this. So part A says, find the total distance traveled for particle q. So if you see two particles in a problem, you got to first, be careful, like which graph or which table are you using, and then also then start breaking down the ideas of what it wants. And so this one wants us to find the total distance traveled. And so before I even look at the graph or information, I would always tell my students, set up an integral for a problem like that. So total distance traveled is going to be the absolute value of the velocity, right, integrated from the limits of 5 to 10. I always want them to set that problem up. A lot of times on AP exams, just that one setup, just applying the formula to your problem and knowing how to set it up is a point. Like that's the first point on a lot of these problems, is knowing which equation or which expression, which integral idea is going to get to our answer. And then once we have that, then we would start computing that. And the idea here is, again, this is a graph of velocity. And so normally, like I was telling you, was doing before, we had all these, shaded regions here, right? And we had one above, and then we had this little piece below, and then another piece below. And what did we do? We would take the positive ones, we would subtract the ones underneath because they were below. Well, that doesn't apply when we have absolute values, because if I just said, what's the integral of velocity, then we would take, a positive, minus, and a minus. But we're doing the integral of the absolute value, which means if we were to think about what this graph looks like, it would actually take these two ideas here and it would reflect them, wouldn't it? Because it would be the absolute value, making things positive. So all the values become positive. So if you're doing total distance traveled and you have a graph, those parts that are underneath the graph, you have to make them positive and instead of subtracting them. So I'm not going to finish out that problem, but I want to lay that down and let you try it, and then you can check our key to see if you applied it correctly. Or if you're a little bit confused still, you can see our worked out solutions and then see what we're talking about by why we're adding those values and not subtracting them. But the one I really want to get to is part B and part E, these last two parts of BC2 part 1, because this is going to re-hit on an idea I mentioned earlier about find the times when the particle is speeding up. And so on the first one, it was kind of scaffolded. I gave you a specific time and I said, okay, is it speeding up or slowing down at that time? Well, here, I'm not going to give you a time, just you find all the times when the particle is speeding up. And so remember, in order for something to be speeding up, it means the acceleration and velocity have the same sign, right? Which means the velocity could be positive and the acceleration could both be positive. Or, right, remember we have two options here, or they could both be negative. And a lot of times this is the part that students forget about, is that they could both be negative. You could be accelerating in reverse. Imagine you put your car in reverse, right? And you slam on the gas pedal, you start zooming backwards. You're still speeding up, aren't you? So since you're speeding up, your velocity is negative and your acceleration is negative because you're pushing backwards. You're going to be speeding up. So you could speed up in either direction. And so we have to look for both of these ideas. If V is positive and A is positive, and we're given a graph of V, that means the graph is positive. So we're above the x-axis. It's a positive graph, and the acceleration is positive. Now remember, how do you find acceleration? That's the derivative of velocity. On a graph, if you're thinking derivatives, you're thinking slope, right? So we're saying V is positive, the graph is above the x-axis, and it has a positive slope. So where on this graph do we see the graph above the x-axis and have a positive slope? That would be right here. This is the only place where both of those things are positive. So we have the interval of 0 to 2. And then finally, we have this other idea, which is V is less than 0 and A is less than 0. So now we're below the x-axis and a negative slope. And that's going to happen a couple of times. Both of those cases, we're going to see the graph is below the x-axis and the graph has a negative slope, which means A is negative, which is going to happen from 6 to 7 and from 8 to 10. So we're going to have a couple different intervals on that one. Now, I want to highlight part E And we're not going to spend much time on because I really want Tony to be able to get to a really cool problem here on the next step. But I really want to challenge you to do a couple of these on your own because they will make a lot of connections with particle motion to other things in A, B, and BC. And part D is a really cool problem, a really nice conceptual problem. I want to put a star by that because that's my challenge problem for the day. That might be one of the hardest problems on this entire packet. So try that one out if you really want to challenge yourself, but don't get discouraged if you're struggling. There's other problems that would be more important and more like what you might see on this year's exam. But part E, I think, is certainly valid for this year's exam, and it involves particle motion, the mean value theorem in a different way than you're probably used to seeing, and Taylor polynomials. So we're telling you not to apply the mean value theorem, but we're telling you the conditions are met on an interval. And then we want to find the second degree Taylor polynomial for the position of particle P. Remember, particle P was this first one, and then approximate the position at time 3. So it's a really cool problem, and I want to leave that for you to try, but I wanted to point it out because it does bring back in those Taylor polynomials and gives you a really good glimpse of how particle motion might be connected to a lot of other topics. We can throw in some mean value theorem and some Taylor polynomials all in one problem. And that'll be worked out solution-wise in the Dropbox. So I want to show you that, but then I want to fast forward a little bit to say, we probably aren't going to have a STEM, a problem that starts out on this year's exam. This is particle motion. It's probably going to be this table and this graph represent kind of a generic idea like we had here, this kind of this initial stem. And then later on in the problem, they might introduce particle motion or other ideas as well. So Tony might give us an example of how this stem might apply to a different topic. So Tony, what do you have for us that we can look at that would address something that would be not quite particle motion, but with the same graph and table?
Well, it follows on the very next page. This is our version of free response question stem recycling. You see the same exact table, you see the same exact graph of G of t, and in fact, the preliminary stem reads the same. The functions f and g are continuous, selected values of f are in the table, a graph of g is shown. But now if you look at the part 2 language, a completely different context. During the halftime intermission at a college football game, popcorn is made and sold at several concession stands throughout the stadium. For time 0 to 10, the rate that boxes of popcorn can be made can be modeled by m of t, and the rate that boxes of popcorn are sold can be modeled by s of t. And both of those are going to be measured in boxes per minute in this case. M of t is equivalent to f of t, and S of t is the absolute value of G of t. So that's where we can kick back in to those two pieces of information, that table and that graph, and use it in a completely different context. It's really cool. Brian did a great job of assembling this. It's one of my favorite problems of this set. T is going to be the number of minutes since halftime began. Both M of t and S of t are measured in boxes per minute, as I said, and at time t equals 0, there are 120 boxes of popcorn. So it's sort of that initial position. Well, it's not particle motion, but it kind of acts as the same thing. And I want to just kind of talk through here for part A. It says, find S prime of 1. And I want to make sure that this shows up. This is a prime mark. It may not show up very well on our slide, but it does show up a little bit better, I think, on the handout. So find S prime of 1 and use correct units to interpret the meaning of that in the context of the problem. One of the things that's really important is that we tell students a lot that we have to know what these functions are in the problem. This S of t, you know, might look like just some normal everyday function, but when it turns out that S of t is a rate, right? In fact, you can read through it and it says the rate that boxes of popcorn are sold is S of t. So it does not look like a derivative, but it acts like a derivative, right? Even though if it doesn't have any kind of derivative demarcation to it. Now, if we're going to take S prime, we are looking at the derivative of the derivative in this case. So notationally, we could say, well, S prime of 1, well, I don't really have a lot of information about where I can take the derivative of just an S in that particular form, but I do know that S is the same as the absolute value of G. So maybe from a notation standpoint, we could think of it like this: the derivative with respect to T of the absolute value of G of T Now I got to be careful because there's a little bit of a linkage problem there. I have on the left side a specific derivative at a point, but on the right side, I have a general derivative. So I could maybe clean that up by using some notation that looks like this, just an option. All right. So now I have to figure out, well, what is the derivative of that absolute value of g at time 1? So I go up to this particular graph. I see at time 1, I do have a point that lies on that graph, but I don't want to call the answer, let's say 40, because that would be the absolute value of g of 1. I want the derivative of the absolute value of g of t evaluated at 1. So I have to look for the slope here. And you've got to be very careful because the scale change could get us into big trouble here. And notice that we have a vertical scale of 10 units and a horizontal scale of 1. So it's pretty clear that we have 10 over 1 as that particular slope. And that turns out to be that numerical answer. Now, as far as the interpretation is, there's a few different ways that you can do this, but there's some key elements that you have to provide here. So what we could say is S prime of 1 represents, well, the very first thing that we like to tell our students is you have just taken the derivative of a rate. Remember, S of t is a rate. So let's start with that word. Brian and I are very similar in that we teach our students to begin in that fashion. Right? So we have this rate. Okay, well, what's this rate doing? Well, we took this derivative, so we have this second connotation of a derivative that has to be embedded into your explanation. Now, you can do that so many different ways. If you use the nut system, maybe we can get into our idea of our noun. So the rate at which popcorn, and I think S stands for the fact that we're selling popcorn, right? The rate at which popcorn is being sold, but I still don't have that other idea of a derivative. So now I could kind of interpret this value, 10 is a positive number. So we could maybe really supercharge this question in this explanation and say that that is increasing. I always like to tell my students, if you have a positive result for the derivative, you have an increase. If you have a negative result for a derivative, you have a decrease. So S prime of 1 represents the rate at which popcorn is being sold is increasing. And then we could put our value in by 10, and the units would not just be boxes per minute. That would be boxes per minute. It would have to be boxes per minute, right? Because we have this second derivative idea. The rate of change of boxes per minute would be boxes per minute per minute. And then we have to make sure that we address the time element, and that would be at time equal 1 minute. Now, are there other ways to do this? Of course. I want to make sure that you emphasize the fact that if you underline those two words, rate, increasing, there's your two derivatives. If you say S prime of 1 represents the rate of popcorn being sold, that will work because you have the word rate in there twice. So you just have to be very careful about some of the language. And as long as you've got the two derivatives connotated kind of verbally, you're going to be in pretty good shape. Brian, I'm going to hand it back to you to see if there's anything that you want to kind of close out with.
Sure, Tony. So I'm going to flip the screen here to my screen, and this is the third tier of the problem. And I'm actually not going to get into this because it wouldn't do it justice to try to do it like in 1 or 2 minutes. We'd be rushing through it, and you wouldn't get much out of that, and then you would lose kind of like the really coolness of the problem. So I think what we're going to do is I'm going to save this problem in its entirety, and then next week is a whole entire week about problem types. So we're going to be looking at just tables one day, how those might appear on the exam, just graphs, with all the different topics. So we're going to take one type of problem, tables, graphs, equations, and then verbal type ideas each day, and think about how all the topics across the course could be asked in those ways. And then Friday, we're going to put it all together next week. So I'm going to save this for Friday because it really does give all three representations. We have a table and a graph and an equation and a lot of verbal components going on. So it's really kind of a neat problem. It's pretty rich. So I want to make sure we do the entire thing, or at least most of it, on Friday. So I'm going to skip over that for now. So even if you're looking at it, if you do it, you might recognize it again next Friday, but you might consider skipping over part 3 of this stem. But it reuses the same table, and it starts off with a logistic problem, and it goes through a lot of examples, a lot of second derivatives, Euler's method, all kinds of fun activities, Taylor polynomials, all in one problem. So we're going to set that for next time. But we do want to flash forward a little bit, like I mentioned, and talk about what's coming up next week. So we just finished day 22. Can you believe you've been attending these for 22 days? I would love to see if anybody has attended all 22. If you've been at all 22 of these, you have to let Tony and I know. We'll put our Twitter handles up here in a second and then tweet out that you've attended all 22 so far. That'd be cool to see who has been here every single day with us. But tomorrow, we're going to be connecting area and volume together, another big A/B topic. And this is something interesting because uh, like today, particle motion, and tomorrow, area volume, those are A/B ideas, but they're not on this year's A/B exam. Now, particle motion will be in terms of derivative ideas, but all the integration ideas, total distance, displacement, position, that stuff is not tested on this year's exam for A/B. And area volume, that unit 8, that includes rate in, rate out, like the popcorn problem that we did today that Tony mentioned, and the area volume tomorrow. Those are things that are excluded from the A/B exam, but 100% they're going to be on potentially the BC exam. And so sometimes we think, oh, we got to just focus on the BC topics. We got to make sure we hit those topics that are A/B ideas, because I think there's a good chance we could see a piece of a question like that as well. And Tony hinted at it today with that one part. We'll do more of that tomorrow, as well as connecting those across the curriculum. And like I mentioned, next week are going to be these different problem types. This would be a really good example each day of how one FRQ can cover just so many different things for the curriculum, how one table could do, here's one big FRQ. So those would be really good lessons. I hope that you'll join us for those lessons as well. As always, if you have any tech issues, the website is there, collegeboard.org/tech. You can pause your screen if you need to write that down and get a hold of it, but make sure that you or anybody that you know has what they need for the AP exam. And then, as everybody mentioned, tweet out to us. We had a couple people, Tony, that actually created Twitter accounts just to tweet out either about their students or about their teachers or about their dogs or just about the lessons we've been doing. So Tweets with Tony is here. And Tony, what do we have today?
Yes, thank you for those tweets, everybody. We were kind of having a pretty dry well there for a while, and now it's full. So we're going to be able to share a lot of these. So keep them coming. AP Teachers Rock. We want to recognize this particular individual. We would like to give a shout out to our calculus teacher, Mrs. Box. She is the coolest math teacher ever and always wears different math-themed t-shirts. She was also the first math teacher to finally tell us that, contrary to popular belief, 0 divided by 0 does not equal 1. Wait a minute. Doesn't 0 divided by, don't the zeros cancel, Brian? Isn't that equal to 1? Okay, I'll have to look at that. Okay, maybe that's an indeterminate form. Okay, and then for AP Students Rock, we're gonna give a little shout out, Mr. Brandon Trainer, Mr. T. Mr. T pities the fools that don't know the chain rule. Luckily, the AP Calc students at Menchville High are safe. They have continued to grind over the last 5 weeks that we have been out of school to prepare themselves. So proud of my Monarchs. So we like to give a special shout out to the students at Menchville High School in Newport News in the great state of Virginia. So keep those tweets coming, and we'll keep airing them and recognize some fabulous teachers and some fabulous students.
Absolutely. And our dog of the day today, and by the way, or cat, right? I know we've got cat lovers out there, right? I might have to show my own cats tomorrow because they're getting mad at me. Dog or cat of the day, right? Today's dog of the day is Derby. Derby is from Megan. She tweeted out Derby, and I've got lots of messages for dog of the day. So if you are, send it to me. Don't worry, I haven't lost it. We're going to work those in, give your dog some love here on YouTube Live. And our Twitter handles are there, at PasswaterB and at AP Calc Teacher. Notice the spelling of both of those. Tweet at us, and we will love to hear about your awesome AP teachers, your awesome AP students, or your dog, cat, fish, whatever of the day. So thank you so much for joining us. Tony, I'm excited for tomorrow. We're going to wrap up a great week, and we're on the down stretch, right?
We sure are, sir. I'm looking forward to it. I'm going to miss it when it's all done, but we still have so many great things to cover. So we want you to stick around. Keep coming back.
Awesome. And Anthony is going to take us out as always.
All right. Stay safe, everybody. Keep learning.
AP Calc, yes, AP Calc. Welcome here to AP Calc, yes, AP Calc.